We are now coming to our second speaker, Babu Ajish, a team lead at the German Research Center for AI in Bremen, so he's not so far away. He just arrived this morning, and he will now give us a more deep dive into robotics, into the cognitive stack. So the floor is yours.
Thank you very much. Good afternoon, everyone. My name is Babu Ajish, and I am a team lead at DFKI, which stands for the German Research Center for Artificial Intelligence, specifically from the Robotics Innovation Center in Bremen. It's close to Hamburg, so I do not travel so much. It's quite nice to be here. So my objective for this talk is to give you my perspective on what is going on in the robotics world, and how AI is transforming robotics world and how it connects to the HPC world. So this is my idea here. So the title of the talk is Perceive, Predict, Perform. And I believe these are the core concepts that's going to define robotics in the coming years or decades. Let's start with what the problem is. So what is autonomy, or what is intelligence for a robot? If you look at it from a high level, so very abstracted out, what is happening here is that a robot needs to see the world. So it has sensors, it sees the world, and it has to take an action. This is conditioned on a goal. So the robot is given a goal, presumably by humans, and you tell them, okay, this is what you have to achieve in this environment. And you have the sensors which you read in, and you extract all the necessary information, take some actions. And when you take the action, the environment changes. This is what we are trying to do as well. This is the high-level part of it. But when it interacts with the environment, things change, and the robot, maybe things happen what the robot did not expect. So if it's intelligent enough, like humans, it will also learn from this experience, and this is a key value for a robot as well, for modern robots. Based on this, we can look at it in three different levels. So you might know what automation is, so what you have in the industry, car manufacturing, whatever applications you see today is pure automation, where there's no intelligence. You just do repeatedly the same task again and again. The environment stays the same. And the next level you can go is to have a little bit of autonomy, where the environment changes to an extent within a domain. So the robot knows how to deal with this uncertainty in the environment, but this is also limited. So if it goes too far, the robot cannot compensate for this. This is where intelligence comes. Intelligence is the capability of the robot, if it's put in a new environment, to learn what is going on, how to interact with it, to solve its problem, to reach the goal. This is what intelligence does. Let's see why robotics is challenging. So we already had the LLM breakthroughs, the revolutions already happened. So now the question is, why is it not happening in robotics? Before that, I'll go through the short history of robotics as such. It started, the first robot started in 1948, which was a very basic robot, some sensors, some analog processing. It had a behavior, so you had programmed the system, and it had some behavior which looks like an animal's reacting. And then the first robot, real sort of sense, plan, act based robot happened in 1966 to the 70s at the Stanford Research Institute, and where the robot could really sense, take a picture, and do some processing, and plan something and act on it. This structure stayed more or less the same for quite decades to come, but there were improvements in terms of the models. Explicit modeling was performed on different aspects. The dynamics were computed, so the robots became faster, more dynamic, could do better tasks. And then came the deep learning, modular deep learning part, where the systems used specifically deep learning for specific applications. For example, it started off with perception. When the environment is so complex, perception used deep learning to identify what is going on in the environment. And this output is taken by other modules to plan how to move around, how to do tasks, etc. But this did not scale well. So this is a complex problem. So the environment is very complex. So now is the time for end-to-end learning where you have the systems which really takes in the data from the sensors, directly outputs the actions on the system. There's no modules involved. There are no separate fine-tuning in the modules, how they are connected, what is the data going through. It's end-to-end. You get the data, sensor data, you output the action. And now, why these challenges come up in robotics? It is hard because one of the things what humans intuitively think is that just moving around, walking around is an easy task. If a 2-year-old can just manipulate, run around, jump, all of these things, we assume it's very intuitive and easy, but in reality it's not. This is because we are supported by millions of years of evolution. Our brain is really fine-tuned to do this. For a robot, this is not the case. It's really hard to do this. But on the other hand, for logical things, which humans really started doing only a few thousands of years, hard logical problem, solving problems, this is very easy for robot. This is the Moravec's paradox. So this explains kind of why robots find it really hard to solve the problems that humans find very intuitive. Next problem is the environment. The environment is very, very complex. So if you look around you, there are infinite possibilities of things happening, infinite things happening. There can be lots of changes. It's continuous. Another big factor is if you take an action in the environment, you cannot undo it. There's no way to undo it. If you fail in something, it fails. So there's no undo button here. This is why it's difficult. And the classical methods, what we had in robotics did not really scale well. So you can explicitly model things, but things change, then modeling is not sufficient enough. And also, here also, if you look at the modular aspects, data bottleneck is there as well. You don't have much data with robotics, so this is also an aspect that is challenging. How did VLA help in this? Vision, language, action model, these are the foundation models in robotics. How does it provide an opportunity? Because the basis of a VLA is the LLM or the VLM backbone, which means it gets all the information what we have, the semantic information of the world provided to the robot. So the robot already knows a lot about the world than it previously knows. So this is a good starting point, and additionally, it provides a natural language interface, so we can interact with the robot quite naturally. Normally, what I used to do was just write codes, write equations, so that the robot knows what I'm trying to do. Now it is not necessary. You write a command prompt, tell do this, and this robot can do this. There are also problems in this methodology. There's data scarcity, and the robots, the models what you train has to run on the system itself, on the edge. These are challenges that I'll describe later on. So this is the whole overview of the whole talk here. We have 3 main modules here: the perceive, predict, and perform modules. So they represent different aspects of the modern cognitive stack of robotics. Perceive is the foundation models, the VLAs, the vision language action models, where it gets the data and it understands what is going on and suggests some actions. Predict is where the world models come in, so it knows then to an extent what is going to happen in the world if I take an action. So it's comparable to a simulation. And perform is where it actually has to do things in the real environment and execute tasks. And you can see that the top part has the cloud part, where you train the foundation models, you train the world models, to an extent also do perform tasks like reinforcement learning. You can do reinforcement learning in the cloud, and you have the basic model that we can use later on. Let's start with the perceive part, the embodied foundation models, the VLAs. So there are 2 key parts to the VLAs. This is akin to the system 1, system 2 thinking. So system 2 is the high-level, slow cognitive process where you understand the environment, plan something and take actions. So this runs at typically 1 or 2 hertz, and this system gets all the input. So it gets all the sensor input, look at the data from the cameras, the joint sensors, LiDAR data, all of this goes in there, and it computes an action. And then this goes into the system 2, which is the high frequency action part, which really outputs makes the robot do action. So basically it sends out the motor commands, what is the current that should be applied in each joint. And here the system 1 is something in literature it's called the action expert. This is because robots don't understand words generally, so you have to send in continuous data there. And the action expert is specifically tuned to connect to the system 1 so that it gets sensible data. There are different variations of this. So one of the ideas that is being used is to do action chunking, which means you don't continuously send data, so you plan for the next few milliseconds, and then you send this at a whole chunk and it will be executed. There are different solutions, so this is an active research field, so things are evolving. But the question is also, how do we train this model? So the whole basis of this is also VLMs. So vision language models form the basis. Most of them do not train VLMs. They take the existing backbone and use it, start from there. So it has already the web-based data in it available on it. Then it uses the robot data, takes the robot-specific data, which is developed or collected using teleoperation, etc., or robot-specific data from other sources, and then it does additional training on it. Then there is action post-training, which basically trains the system 1 action expert to perform basically diffusion-based controls, or sometimes also flow matching as well. So this is an example of one of the most modern VLAs from physical intelligence. So you can see that a robot is picking up a sweet potato and putting it in an air fryer. As such, the video is not impressive. If you just look at it, you have seen more complex things done by a robot. But the fascinating part here is this robot in the training data does not have any samples regarding this. It doesn't know what a sweet potato is. It doesn't know how to use an air fryer. They explicitly did not have any teleoperated data based on this. So it was able to generalize. How it did was, it had a vague idea of what air fryer is from its some web content. But what it did was it used some tricks. So composition is one trick that they use. So they used all the data, and it could compose some solution based on the previous experiences or previous data they had. And the second one is to get help from an operator. A researcher just teleoperated it for a few minutes. This is important, but it's only a few minutes of teleoperation, and the success rate without the help was 5% and then jumped to, 95%. So this is a real boost. So without a new scenario, within a few minutes, you can make a robot learn a new task. And this is generalizable as well. So you can put the air fryer in a different position, it will adapt to it. So this is a video from Gemini Robotics, so where you can see the robot doing quite a lot of interaction with the environment.
Can you put the bananas in the clear container?
So there is lots of interaction, the things change, the environment changes, it's able to do that. And you have to also imagine that robot is interacting with different types of object without explicitly telling how to do this. This is something it was really, really hard to do before, but the VLAs find it really easy to do this, and they can adapt very well. So what it shows is that the VLA architecture is kind of converging. There are lots of common modules that can be used. Now we'll come to the second core, which is the predict part, so predictive world model. So if the robot can predict what will happen if it takes an action, this is a huge advantage. Then it can do lots of things. And for that, world models are being developed. And this will help a lot. So there are two types of basically world models where it can generate pixels or it can generate encoder latent space world model. So the difference is that one is good for video generation, the other one is good for really having compact representation for the environment you are. It's as easy as taking a photo and then it can automatically generate the world for you. And what happens here is you can take the input, depending on whatever input you have, you can put all of them in, it'll be in a particular encoded space. And the important part is also the dynamic model. So you have the dynamic model that is also extracted from this, and which you can use to try something out and then see what is the best way to go forward. Then you can predict what will happen and do this in loop until you have an imagined future. So you are literally dreaming about what will happen. This is very akin to what we will say, okay, if I do this, this will happen, so I'll do this. This is not a good idea, something like this. So this is the VJEPA world model, which is developed by Meta. What it does is it has a screenshot of what it starts off where it should reach. In the middle, you can use the world model to plan what should happen in between. So it does different planning, tries different configuration, tries different latent spaces, and then you have an idea where it will end up and how to go through this. Similarly, NVIDIA also has similar solutions. The NVIDIA Cosmos, you can just
using a single image and natural language, developers generate synthetic world states or dreams.
So just have one image and you have a representative data in your
but prompting with natural language has its
which the robot model can use to try things out. So this is quite powerful. You can also collect data for teleoperation as well. So what can we use the world models for? So primarily you can use it as a planner. So you can plan different things out and take the best plan. You can use it as a data engine to generate more data for training. Sometimes you don't have good quality data to train a huge network, then you can have synthetic data with this. You can have a unified model where the actions and the output share a same network. So they are consistent, they have consistent representations. You can also use it as a simulator to stress test your policy as well. Now we come to the third part, which is the perform. This is where the robot interacts with the real world. How do you interact with the real world? VLS generally don't have the explicit data with which it can interact with the real world. Things change when you interact. Most of the time you don't have, for example, no for-stock data of the robot, so it doesn't know how much, for example, opening an air fryer, it doesn't know how much force to apply. This is something it has to learn from the real world. It has a guess maybe, but it doesn't know exactly what to do. So the pipeline currently is to train in simulation, so you can train a robot in a cluster. Thousands of parallel runs can be executed in a time, and then you have a basic trained system. And then you have to transfer to a real system. There the huge problem, sim to real gap is coming up. But there are methods to solve this. But there's also a huge improvement on the execution on the robotic side as well. So you can show, humans can demonstrate how to do it if it's a complex task. And then another way is to coach it. So you can verbally tell it what to do. If taking example of the air fryer, you can tell them, first grab the handle, now pull it. This coaching helps a lot. So this is very good, especially when it makes a mistake. This is very valuable data. If there's a mistake, you interrupt and then correct it. This is very valuable. And then autonomously, the robot can by itself execute it in the environment. All this can be combined to form something called an advantage condition reinforcement learning to get very good results. So one example is the Atlas robot. this is completely learned from reinforcement learning. So this is a complex system with huge dynamics, huge interaction with the environment. There is some data coming, lots of data coming from the motion capture, etc. But once it's trained, it's quite able to do this with zero shot. There is no reinforcement learning happening on the system. This is done just in simulation. And then it does really complex motion. And here's another example where on the left side you can see the robot doing, just from the VLA policy, it's taking a long time to execute something. Then you train it for a few minutes on the system, and the system is able to execute the same task. This is a highly complex task for a robot, and it's able to execute it in really fast. Reinforcement learning provides the possibility to post-train a VLA policy, or you can have low-level skills which needs huge amount of interaction. You can connect it to the world model and train it from the world model, and also of late there are foundation models which help the reinforcement learning to train properly. This is the data pyramid. So the idea here is to show how data is being used. So most of the data is highly dependent still on world web-based data. And the teleoperation data is quite limited now, which is improving with time. So now the HPC. So what is the real problem here? So the training, most of the foundation models are trained in the cloud with huge amount of training budget available, energy, GPUs, etc. But it has to run on a mobile system which has limited computational capacity. And here we can see the frequency with which most of this executed, the models are executed. And so this also shows that on the actual system, you have to limit the model size and the frequency as well to get a good system running. So now let's recap what happened here. So what are the real things that happen? So now the language basis can be used for action. So there's the LLM models has been connected to the robot, and it can really perform actions. This has been proven by a number of VLA models that's been developed. Cross-embodiment is possible. The same model works for different physical systems. This has been achieved as well. Learning from real robot experience has improved so much. And this is also a good point for robots to be used in the real world. And world models are also helping to accelerate all of this forward. Massive parallel simulations are also helping a lot. So most of one example is the animal robot, which can be trained in a GPU with, in 2 minutes, it's able to learn a real walking pattern. So what is still hard? So what are the problems and challenges it's facing? Reliability and long-term robustness is a huge problem. Lots of things are still in research. So we don't know how it really performs in actual scenarios. It's totally new world. If it's totally new environment, how does it perform? We don't know yet. And data limitations are a huge problem as well. So we don't have much robot data. There are opportunities there, but still is an active field which can be solved as well. Generalization to unseen objects and scenes, there are solutions to it, but still there are lots of areas to be covered here as well. Real-time on the edge, this is a huge problem that is still actively being researched. This is a real hard problem as well. So the models are small, so it cannot incorporate all the things that you expect a model to incorporate, and also this delay is costing us. There's active research going on. Probably better architecture, better models can help in the future, but this needs to be solved as well. And for me, I think the biggest bottleneck is the safety verification and guarantees. Currently, the neural network architecture doesn't have any guarantees, any safety things. You don't know when it runs end-to-end, when it stops working, what are the limits. when it is going to fail, we have no idea. The field is developing so fast that we have to explore this in research as well as in practice as well. Thank you for your time. If you have any questions.
Yeah, thank you, Babu. All right, so we would have time for one question. Somebody from the audience? Okay, I don't see anything online as well. So you talked about world models, and we have seen also different sizes. Where do you see the trend? Will these world models always increase in size again? And do you see that we will also develop some world models in Europe, or do you actually also plan to develop a world model at your institute?
Developing world models need scale. So currently, as far as I know, we don't have the necessary infrastructure to do this, and also the data. So this is an open problem. So I think this is possible. The willpower is there, actions are being taken, but it might take some time before we see a world model from Europe.
Okay, good. Then thank you very much, Babu.
Thank you.
Yeah, and with that, we would like to close this session. Thank you for attending.